So far we have taken refraction on plane surface, and we have seen, we calculated the relation between so far we have done refraction on a plane surface, and we derived an expression relating the apparent depth and real depth of a swimming pool. Now, if we take a curved surface, so it may be convex or it may be concave. Suppose I take a convex surface, single surface. So, single surface means it is not a lens. Lens has two surfaces. So, I am considering the refraction on single curved surface. N1, N2, refractive indexes of the two medium, and let us say N2 is greater than N1. So this medium is denser than this. Then C may be the center of curvature of this surface, curved surface. A spherical surface we are taking, so this will be the center. Let O be a point object. Consider any one light ray, this one. One we may take straight, so it will pass through. Angle of incidence 0, so angle of refraction is also 0. What about this? Draw a normal. This is normal. So this will be the angle of incidence. Incident ray, normal, a line passing through C, and the point of incidence. I is the angle of incidence between the normal and the incident ray. And now it is, the ray is moving from rarer to denser medium, so it bends towards the normal. I am taking a case of real image. Otherwise, it may also happen that the ray bends slightly but does not cross this principal axis. That's also possible. In that case, ray will be extended and we will get an imaginary image. But here, I have taken the real image. So this is the angle of refraction. This is refracted ray. Incident ray, let this point be N. This point be P. ON is incident ray, NI is refracted ray, O is point object, I is image, and this is normal. Angle of incidence, angle of refraction. Now to relate these distances, OP, PC and PI, N1, N2, we will find an expression. There are certain assumptions to be made. So first note down them, and those assumptions are, we will take curvature is small. First assumption, curvature is small. We will deal with paraxial rays only. So if this is small, the rays will be close to this. Further, if I draw a perpendicular here, this distance is to be ignored. So radius of curvature is large, this point very close to this, so this distance will always be very close to 0. Okay, so I will ignore this distance, paraxial rays, and one more, angles involved are very small. I and R very small, so if this point comes very close here, then this angle will be very small. I and R very small. Basically, we will take I as sin I and this as equal to tan I. We will be using this. For small angles, sin I equals I, tan I also equals I, sin 0 is 0, tan 0 is also 0. For small angles, we may take them. So one, this angles is small, aperture is small, paraxial rays only, and this distance is almost 0. Okay, now let us take these angles, alpha, beta and gamma. Alpha, the angle which the incident ray makes with the principal axis. Beta, the angle between the refracted ray and this line, and same way gamma. Now let us apply Snell's law. N1 sin I is N2 sin R. For small angles, I will just write it N1I is equal to N2R, N1 and I and R. I will take them as 10I and 10R. Okay. Before that, now alpha, beta and gamma. Let us relate these angles with I and R. You can see from this triangle ONC. ONC. I is equal to alpha plus gamma. Exterior angle is equal to sum of two interior angles. And same way in triangle NIC, gamma is equal to R plus beta. Here also these two interior angles, this is the exterior angle. So in this triangle, gamma is exterior angle, this is equal to R plus beta, and in this triangle, I is exterior, this is equal to alpha plus gamma. I will be using these two here. So N1, I is alpha plus gamma, N2, R is gamma minus beta. R is gamma minus beta, I is alpha plus gamma. And now let me write alpha, beta and gamma in terms of these distances. Alpha, which can also be taken as tan alpha. So alpha is Nm upon this, and I will take M as same as P. So I am taking Np as 0. So it means M and P, I will be taking them as same point. So tan alpha will be Np upon OP plus, or you can write Nm upon OM and then M as P. Gamma, this by this. So Np upon Pc is equal to N2 gamma, again Np upon Pc minus beta Nm upon Mi, and M is P, so upon Pi. Okay, Np is common to all, so we can remove it. We have N1 1 upon OP plus 1 upon PC is equal to N2 1 upon PC minus 1 upon Pi. Two terms have PC, so let us take them on one side and another one on one side. So N1 upon OP plus N2 upon Pi is equal to N2 minus N1 upon PC. I have taken this term on this side and this term on this side. Okay. You should write these steps yourself to understand it better. N1 upon OP plus N2 upon Py is equal to N2 minus 1 upon Pc. Now I will write them, instead of writing in terms of P, I, O, these points, I will write it in terms of U, V and I. That will make more sense. out of this expression. And with proper sign convention. So we will make it general expression. Now for whatever surface, let us first write it. Okay. N1 upon OP. What is OP? Minus U. Distance is to be taken from P in the direction of incident ray plus opposite to the incident ray minus. Incident ray is left to right. So U will be negative, R will be positive, V will be positive. Plus N2 by Pi V is equal to N2 minus N1 upon R. So N2 by V minus N1 by U is N2 minus N1 by R. This is the final expression relating refractive indexes of the two medium, radius of curvature of the surface, distance of object and distance of image. We have already done it for plane surface. So if I want an expression relating U and V for plane surface, what should I do here for this expression? Replace R by infinity. So this will be 0 and N2 by V is equal to N1. We will get real depth and apparent depth relationship in terms of N1 and N2. Now here the object is in rarer medium. Right? So real will be less than apparent. So real will be this, apparent will be here. N2 by V and 1 by U. We'll get a relation here. Okay. So this is a relation for refraction on curved surfaces. Now we will use this expression in lenses. Lenses have two surfaces, and before that I shall like to tell you that we have derived this expression specifically for convex surface and that also for real image. But this expression is equally valid for all types of curved surfaces, spherical surfaces, whether it is concave or convex or the image is virtual or real. But you will use it with proper sign convention. That's it. Other cases you may try yourself. You may draw a diagram for virtual image, for convex surface, and same way you can take even for concave surface. Okay, that's it. Now we shall be using this expression for deriving a relation for focal length of lenses. In a lens, we have two surfaces. At least one of them is curved. How we define a lens? So lens is a transparent medium because it works on refraction principle. It's a transparent medium bounded by two surfaces. At least one of them needs to be curved. So it is not necessary that both the surfaces are curved. It may be like this. It may be like this, or it may even be like this, or it may be like this, or it's also possible that it is like this. Okay, what about this? This is not a lens. Okay, lens does not have the uniform thickness everywhere. So it is simply a plain glass plate, though it is curved. It is just like glass bottle. You take a glass bottle which is having cylindrical shape and you break it. So every part of it will be curved, but having equal thickness. So it is not a lens. For lens, the thickness should not be uniform. Simple way to keep in mind. This is a glass plate with zero power and infinite focal length. Our sunglasses are like this only. Okay, so this is lens, and same way all these are lenses. This is, we call it double convex or simply convex or biconvex. This is concave. This is plano-convex. One surface plane, one convex. It is plano-concave. It is concavo-concave, concavo-convex. One surface convex, another surface concave. So concavo-convex, that's also possible. Okay, now let us see what is the result when light rays strike a lens. It is made up of a material having higher refractive index than air. So if I take a light ray here, okay, now this is a curved surface, so it will have some center of curvature. Let me say it C1 for this surface. So okay, I may draw a normal like this. Okay, so the light ray is moving from rare to denser, so it comes closer. Let me take like this. Now again, at this point, this is curved, so this will also have a center of curvature, but this second surface will have center of curvature on left side. First surface drawn from this side, second surface drawn from this side. So again, let me draw a normal at this point. And now it is moving from denser to rarer. So it may move denser to rarer, away from the normal. It is normal, so it has come earlier, rare to denser, closer, and then now again it is coming towards this, actually away from the. So maybe like this. First surface brings it slightly down, another surface further brings it down. Now imagine the situation if N2 is less than N1. Let us see what happens if N2 is N2, N1, N2 less than N1. Normal, C1, it moves away from the normal. So it will move somewhere here. And now again, so it is moving in this direction, but it will come closer to this, so it may move like this. So the same shape, convex, may act as converging lens. It may also act as diverging lens. It depends on the relative values of refractive indexes. If the lens is made up of a material having refractive index higher than the surrounding mediums, it is a converging lens. And if it is made up of a material having refractive index less than that of the surrounding medium, then it is a diverging lens. The same way we can work out for even concave lens. Concave also, it will be diverging normally if kept in air and made up of glass, say. But again, if it is made up of a medium having refractive index less than that of air, then concave lens will act as converging lens. But normally when we say converging lens or diverging lens, we generally mean that the lenses are made up of glass and they are kept in air. So converging lens, this term is used for convex lens. Diverging lens is used for concave lens. Okay, now some basic definitions related to lenses. Concave as well as convex. Okay, this is concave, this is convex. Just like mirror, we have here center of curvature, but there are two surfaces. So there are two centers of curvature, one for this surface, one for this surface. So centers of curvatures, centers of that part of which this particular surface is made up of. So two surfaces, for first surface, C1 on this side, second surface C2 on this side. For this, C1 on this side, C2 on that side. And same way we will have radius of curvature, so two radii of curvatures for this, for this. This is called optical center of the lens. And one very important definition is focus. And by focus we mean, see now, instead of showing the refractions on both the surfaces, we'll deal with thin lenses. For all ray diagrams, we will take the refraction, we will show the refraction only once, and that usually from the central line, instead of showing it at both the surfaces. Otherwise, refracting action actually occurs at both the surfaces, and it is a converging lens, so it will bring these rays closer. So that point which makes these rays parallel to the principal axis, this is the principal axis, that we call the focus. So focus is a point on the principal axis. Focus is a point on the principal axis. Same way. And what it is doing, that if the object is capped here, the rays will become parallel. What about concave? When will the rays be parallel? It is a diverging lens. Suppose the rays are going, it will diverge them. It is the diverge. They were coming in this direction, so it has diverged them. And where were they going? They were approaching to this point. So here, this is the focus. Right? And there is another way of defining focus actually. This is, we call it principal focus or first focus. I'm giving you one more situation, just think what will happen. If the rays are coming parallel, now what will happen? They will come at one point. This is focus, this is also focus. This is focus and this is also focus. This is called first focus and this is called the second focus. However, whenever we are talking about focus of a convex lens, then we usually mean this. Focal length will be the distance between the focus and the optical center, the distance between the optical center and the focus. So this is the focal length. How can we define this focus? A point at which the rays initially parallel to the principal axis converge after refraction from the lens. A point on the principal axis from where the rays initially parallel to the principal axis appear to come after refraction from the lens. This is how we define this focus. And focal length, this distance, sign convention I told you here also same as for mirror. So if the distances are to be measured from O, and if the distance is in the direction of incident ray, it is taken as positive, opposite to the incident ray, it is taken as negative. Here it is in the direction of incident ray. So focal length will be positive. Here focal length will be negative. Focal length for concave lens is taken as negative. Focal length for convex lens is taken as positive.